Hello everyone, welcome to the first class of Math 473. Today I'm going to review the basic probability and statistics. There are the prerequisite courses that you should, knowledge that you should have, which includes integral calculus, differential calculus, and algebra limits. There is a section in the Coaching Actuary website for the ASTM class. There is a section called Prerequisite. Then there is a subsection called Math Foundation. I strongly encourage you guys to read through that section. If you are not familiar with all those prerequisite courses that I just mentioned, but today I'm just going to focus on basic probability and statistics. So as we know, there are two types of random variables. One is discrete, one is continuous. I put them side by side so that it's easier to compare and understand it. So for discrete, it takes values from a specific set of exact countable values. For example, it can be value be 1, 3, 5, 6, 7, but it's countable value. For continuous, it's take values from a specific interval or collection of intervals, then it's not countable. There are unlimited number of these values there. And correspondingly, there are two different ways to find the probability of these values. One is using, for discrete, we are using probability mass function, PMF, while for continuous variables, we have to use probability density function. So for the discrete random variables, if a random variable x is discrete, then for any value x, the probability of x can be calculated by evaluating its probability mass function PMF at x, which is commonly denoted by one of the following. You either can say probability x equal small x or p parenthesis x with subscript x or without a subscript x. While for the continuous random variable, a probability density function, or density function for short, is the equivalent of a PMF for continuous random variable. For continuous random variable x, is a PDF denoted as fx with subscript x or not. They are representing the same thing. And lastly, for the px, the value of px, if it's discrete, we know the value is between 1 and 0 and 1. And for the continuous, the fx, the PDF, the probability density function, is always greater than 0, but greater or equal than 0. Okay, now if you for the probability mass function, if you sum all the probabilities, it will add up to 1. But for a continuous random variable, you cannot sum them up. Rather, you use the integral. You integrate it from negative infinity to positive infinity. Then you will get a total equal 1. That's the difference between discrete and continuous. So basically, discrete, you sum them up, sum all the PMF up. For continuous, since it's a probability density function, you don't sum them up, you integrate that together using the integral, then you will get the total. Once we have PMF or PDF, then the next function that we can calculate is a cumulative distribution function. So the cumulative distribution function CDF, also called just called a distribution function uh, of a random variable x, is the probability that x does not exceed a given value. This definition holds true for both discrete and continuous random variable. The CDF is commonly denoted by one of the following. So its probability of bigger x is less than or equal to small x. Or we can also note it as bigger fx. The CDF, the cumulative distribution function, is calculated as the sum of all the discrete random variables and as an integral of a continuous random variable. That's the two formulas showing here. Okay. Once we know the CDF, the next function we will know is the survival function. Survival function is basically the complement of the CDF. So you can see for CDF, probability is x less than or equal to small x. But for survival function, probability is x greater than small x. And similarly, it's denoted as capital SX. So based on this definition of survival function, we know that survival function Sx is just 1 minus Fx. Then from there, we can use the same formula to derive the value of Sx. The next function that we can derive from the function we just learned is the hazard function. The hazard function, commonly known as the hazard rate or the force of mortality, is the ratio of the PDF of a random variable to its survival function. This is only applied to continuous random variable here. So Hx is equal Fx. Fx is the PDF over Sx. Ss is the survival function. So then, using the definition of this Fx, which is the derivative of negative of derivative of Sx, then we can derive it to become Hx is become this final one here. Okay, so this is the function for hazard rate. Now with the hazard function in mind, we can calculate the cumulative hazard function, which is basically just integrating the hazard function to produce the cumulative hazard function, which is often denoted as capital Hx. So based on what we have earlier, we can just integrate this hazard function to be this was from previous slide. Then eventually you get a natural log of Sx. And from there we can derive Sx is equal e to the power of negative Hx. For those of you learn the theory of interest, you might recognize this is somewhat similar to what we learned for the force of interest, where you have a rate of interest, force of interest, and the calculation is very similar. The next concept that I'm going to review is percentiles. The official reading defines the 100th percentile of a random variable x as the value pi p that satisfies both of these inequalities. Probability of x less than pi p will be less than or equal to p, and the probability of x less than or equal to pi p will also be greater than or equal to p. So in this case, basically they are saying the f of pi p is just equal p. In other words, the 100th percentile of a continuous random variable x is the value pi p that satisfies the f pi p equal p. And okay, then there are some special names for certain percentile. The 25th percentile is the first quantile. The 50th percentile is the median or the second quantile. Similarly, the 75th percentile is the third quantile. Here you need to understand the 50th percentile is the median. You need to remember the concept of a median, because later we will learn the concept of mean. Based on this, we can say that median is not always the same as mean. Okay, now let's look at this example. This example is about a continuous random variable, and let's read the question first. A random variable x has the following probability distribution. Fx, small fx, is equal 0.5x, where x is in the interval of 0 to 2. Determine the median and the third quantile of x. So we know the median is just 50th percentile of x, and the third quantile is 75th of them percentiles. The first step we have to do is to calculate the CDF based on the fx is given. So let me see. Okay, fx would equal this 0 if x is less than 0, and do this 1 if x is greater than 2 or equal to 2. Now the middle part, the CDF is just for this continuous random variable is just the integral of 0.5. So integral of 0.5 is 0.25 x squared. So if x is in this interval, this is the CDF. Now with this, we can calculate so first f pi 0.5 is equal 0.5, which is equal 0.25 x squared. From there we can get x is equal square root 2. Okay, similarly f pi 0.75 will be equal 75. So from there we can get x equal square root of 3. And just look at this function itself, you will see that this function fx only has a value starting from 0, then it's going up until it gets to the 0.5 point. Then it keep increase until it increase to 1. Then from there it's just flat. From here it's set because it reached the maximum value 1. Now let's look at the next example. This is an example for percentile, but it's for discrete random variable. So the question is, a random variable x has the following probability distribution. Px equal 0.4 if x is equal 1. So it means the probability for x equal 1 is 0.4%, and probability of x equal 2 is 0.2%. Probability of x equal 5 is 0.15%. Then probability of x equal 8 is 0.25%. Then otherwise it's 0 possibility. Determine the median and the third quantile of x. For the discrete example, the best we can do is to draw the graph first. since it's discrete, so there isn't many points, so it's very possible you can draw everything out. So here you can see that x equal 1, this point, there is 0.4%. So here, let's, okay, it's here, 0.4% here. Then when x equal 2, that's 0.6%. So when we look at that, then 0.5% is in between. So, which means the medium is 2, because this is where the 2 is, it meted 0.5%, 0.5 here, or 50%. Then when it gets to 0.5, x equal 5, you see the probability is increasing to 0.75. But the next jump is actually at 8 when it's reached the maximum fx is equal 1. So in this case, 5, 6, 7, 8, they can all be the third quantile of x, because 0.75 is matching every point in here. That's the so the difference between continuous and discrete is that for discrete, you might have more than one value for a median or for a certain quantile, and for the discrete, you most likely you want to draw the graph and find out the value. But for the continuous, you just mostly you just need to do the integral. Then you will be able to solve the equation to get to the number you want. The next concept we are going to learn is mode. The mode is the value of the random variable that maximizes the PMF or the PDF. In other words, the mode is the critical point of the global maximum of the PMF or PDF. For continuous random variable, the mode is easy to calculate. Maximize the PDF means calculate the first derivative of x and equating it to 0, then solve for x, which is the mode. So basically, you set f prime x equals 0, then you solve for x, which is the mode. But there's one caveat though. Is this f prime x equals 0 the only condition for mode? If we recall in calculus or in algebra, I don't know which class you took for regarding this, but generally the global maximum, if we draw a function or variable, say it's like this, then we know to find the global maximum, normally we do a line, we call this a tangent line, that is just touching the highest point here. Then we have this tangent line function is f prime x equal f prime x. We set it equal 0, then we can calculate x. But this is another possibility where you have a function like this, right? Then you can have a f prime equal x. So when you do the tangent line, which is the first derivative of this function, you can find a value, but is this the global maximum? No, this is the global minimum, because every other point is greater than this, right? So basically it has another requirement. Other than fx equals 0, you will also need to have a f prime, the double prime, the second derivative needs to be less than 1. That's the complete requirement, but generally you don't need to consider that. Most likely you just need to be using this to be able to get it. But bear in mind, in the complete theory, if you want to find a global maximum, you not only need to have a least function, you also need to require least. Otherwise, you may not end up with a max. You might end up with a mean here. That's just a little more knowledge that we need to know. Now let's look at example for this mode. The problem is a continuous random variable x has the following PDF. Fx is equal this, and determine the mode of x. So this is the fx function. Now we need to determine the mode of x. So from what we learned earlier, we know to determine the mode of fx, you will have to first calculate the first derivative of x, which I know is 0.75. 1 will be 0, so nothing there, times negative 2, x minus 1, so it would be x minus 1. Then it will be 0.5, put it to the front, x minus 1. And if you want to put this to be 0, then x equal 1. And to check what we earlier said about it, the f prime x has to be less than 0 in order for it to be maximum. So let's just calculate f prime x for the sake of it. F prime x is, take another further derivative of f prime x, is 0.5, which is less than 0. So, okay, we solve this problem. The next concept that we are going to review is moment. And there are two different moments. One is raw moments, one is the central moment. So for raw moments, the case raw moment of x, or the case moment of x for short, is defined as mu prime k equal e x to the power of k. So it means it's the expected value of case power of x, x to the case power a, x raised to the case power. This is raw moment. When k is equal 1, we know it's just the expected value of x, which we also denoted as just mu. So mu prime 1 Ross moment. The first raw moment of x is denoted as mu prime 1. It's also just mu, which is just the mean. It's the mean because it's just the expected value. Now, how do we calculate this expected value? We know in the past, or from what we learned before, that ex is, if it's discrete, use sigma x times px. For each x, you have a probability PMF probability mass function. Then you use this, you sum it up. This is for discrete. But if it's continuous, you use the integral. You integral x times probability dense function, and that's how you get the ex, expected value or mean. Now the central moment is just instead of expected value for x, you use x minus mu, where mu is the central moment, which is the mean of x. Mu is the mean of x. So that's the difference between raw moment and the central moment. We learn mean is the first moment, and now we learn that variance, which is the most well-known central moment, which is second central moment. The definition is mu2 or variance x is equal this e expected value of x minus mu raised to the second power, and you can also note it as VAR variance, or you can omega squared. That's how we denote that. The function of mu is to tell us how the data or this random variable is away from the variance, away from the central mu. So if you see, in this graph, you see that for the red line, it's narrower. It means it has a smaller variance because every value is closer to mu, to the central mu. And the other one, the blue line, has a larger variance because the values are further from the central, from the mean. That's the use of variance. Here are some very important formulas for variance. First, we derive this variance VARx is equal E x minus mu squared. Now we can extend this x minus mu squared to be this. Then based on the expected values property, you can apply E to each of these items. So E x squared minus 2E x mu plus mu squared. Further, you can consolidate it. So it's basically just VARx is EX squared minus EX, the whole EX squared. Note the first node is the expected value of x squared. The second item is the expected value x, the whole thing raised to the second power. And we can also generalize this property to other functions. So we have this. For any function gx, the variance would be first you use the expected value of gx squared minus of the whole thing, the expected value of gx and the whole thing raised to a second power. Further, variance has 4 more important properties that are useful. So first one is if it's constant, your variance always be 0 because there's no variance for a constant. And second, if its variable is x plus c, then based on the first rule, variance c is equal to 0. So basically, they have x plus c has the same variance for x. But if this c is multiplied by x, then when you pull it out, it becomes c squared because variance is the second power raw moment, second central moment. And the last one, variable ax plus by, this one is a little more complicated. It not only has the variance for first term x, and also have a variance for the second term y, and also have a covariance here, where COV xy is equal this. This is some formulas that you probably will encounter or will need to use in the exam. So the best thing is you memorize it and apply it in solving your problem. Next two concepts is related to variance. The square root of the variance is the standard deviation, which is often denoted by omega. In the case of multiple random variables, subscripts will be added to omega to distinguish between the random variables. The second one is the coefficient of variance. Coefficient of variation is just the ratio of the standard deviation to the mean. In other words, it's calculated the standard deviation per unit of mean. Basically, it's omega over mu. These two concepts should be simple to understand. Earlier, we talked about the first moment and the second central moment, which is variance. Now we are talking about the third central moment. The third central moment can be used to calculate the skewness of a distribution, which equals the third central moment divided by the standard deviation cubed. So skewness is equal mu3 over omega to the third power. It's usually more practical to compute the numerator mu3 by expanding the expression for the third central moment, similar to how we derive our default variance formula above. I'm not going to derive this formula, but I think one thing, the formula that you are going to use to derive this is this, a minus b, so it would be equal a This is the formula that you should use if you are interested in deriving this formula, but otherwise you probably just need to memorize this. Skewness is used to determine how the distribution, whether the distribution is symmetrical or not. So if it's zero skewness, it means the distribution is perfectly symmetrical. One normal example would be the normal distribution. As we know, it's just a bell shape and it's symmetrical. Positive skewness means the distribution is right skew, suggesting a longer right tail. This implies smaller values are more likely to occur than larger value. Negative skewness means the distribution is left skewed, suggesting a longer left tail. This implies larger values are more likely to occur than smaller values. This graph just shows how to interpret this skewness. If its skewness equals 0, it's symmetrical. If it's right skew, then you will have a positive skewness. If it's left skew, you have a negative skewness. We talk about the first moment, the second central moment, which is variance, third central moment related to skewness. Now we are talking about fourth central moment, which is related to kurtosis. The definition of kurtosis is the fourth central moment divided by the standard deviation to the fourth power. So the concept is very similar to skewness, but the kurtosis measure the flatness of a distribution. It suggests the likelihood for a distribution to produce extreme values or outliers. The normal distribution has a kurtosis of 3. A distribution with kurtosis greater than 3 is more likely to produce outliers than the normal distribution, and vice versa. Also, for the mu4, we can use this formula to calculate it. I think the formula is, if you want to derive it, similar, but we don't need to do this. Okay, let's look at this example. A random variable x has the following density function fx is equal x over 8. X is in the interval 0 to 4. First calculate the coefficient variance of x. Okay, we are given the density function, so what we can do is, first step is we calculate the ex or mean. Ex would equal, according to the definition of ex or first moment, will x times fx, which is x over 8, and accumulate between 0 to 4. Then from here we can see this is equal x squared over 8, but when you integrate it, it becomes x to the third power x to the third power over the 3 times 8, just to keep it. Is from 0 to 4, which x to the 4 to the third power is 64. 64 divided by 8 is 8, and so we got 8 over 3. Similarly, we are going to calculate the ex squared, which is just this x squared times 8 dx, which would be x 4 to the fourth power over 4 times 8, which will be 8. Yeah, okay, it's 8 somehow. Okay, now variance. Let's get next step will be calculating the variance. VARX, we know from the formula it's equal EX squared minus EX from what we learned earlier, and this square is outside EX squared. So from here we know EX 8 minus 8 over 3 square. So this we can get is equal to 8, 9. And after this, the next step, we can calculate the finally we can calculate coefficient, which is equal, we are x square root, we are variance over ex and square root of over ex, which is 8 over 3. Then this can be 0.3536. Okay, so we get the coefficient of the variance. Similarly, for the skewness of x, first we need to calculate the ex. Let me see, ex to the ex cube. Then you will be able to calculate that. Skewness is just the using the formula that was given in the previous. I'm not going to write it down. If you are not familiar with this, or if you want to calculate that, you can also follow the coaching actuary. This part is on the coaching actuary, so please do it yourself. We will get the result to be skewness is to be 0.5657. Negative 0.5657 is the result. And for the last one, the kurtosis, the result is 2.4. So the second question is 2.4. All you need to do is follow the formula and calculate the ex to the false power first, then you can use the formula to get to the final answer. Yeah, check the coding actually if you are not 100% sure about this part. I'm limited to the space. I cannot write more. Okay. The next topic is empirical distribution. The empirical distribution is a discrete distribution based on a sample of size m that assigns probability 1 over m to each data point. Let x1, x2, and xm be a sample of size m. The empirical distribution function is the CDF of the empirical distribution. It's calculated as the proportion of observations no more than x out of m total observations, meaning fnx is equal number of observations less m x over m. We can calculate the empirical 100th percentile the same way we calculate the 100th percentile for discrete distribution. Because all m observations are equally likely, the empirical 100th percentile reduced to m-pth order statistics of the sample. And in general, the empirical expected value can be calculated using this formula. So basically, your expected value for gx is just sum all the small gxi together and over m. The empirical first raw moment is called the sample mean and is denoted as x bar. The calculation is very similar to calculate the average or expected value. You just sum them up, you divide it by the total. And the empirical second central moment is called bias sample variance. The concept is still very similar. Xi minus x bar, you square, then you sum it up, then you divide it by m. Here we need to be careful. There's another concept, the unbiased sample variance has a divisor of m minus 1 and is denoted as square, s squares. S square is the same in the numerator, but it's m minus 1 in the denominator. So this we need to be careful. Generally, it's going to be confusing, but general rule of thumb, if we're talking about empirical distribution, normally we should use unbiased sample variance. So you use the last formula. But in other cases, if it's not talking about empirical distribution, most likely we'll just use the biased sample variance, the second formula here. Now let's look at this example. You are given a sample of size 6, 1, 4, 5, 8, 8, 10. Calculate the empirical distribution function, evaluate at 6. So first question is just ask, how do we interpret this question? It's basically just ask f6 equal number of observations less than or equal to 6 divided by 6. So here we see that 1, 4, 5, so there are 3 numbers less than 6. So this is the answer for the first question. The second question, the empirical 75th percentile, as we said earlier, in pi mp. So basically we are just doing it's pi mp. P is 75%, but 75% times 6 is actually 4. So it's really asking about 4. Now we see that the fourth element here is 8. So 8 is the answer. The third question is asking the skewness of the empirical distribution. Of course, to calculate anything skewness or variance, we have to calculate x first. So first we calculate Ex, which is just adding them all together. Over 6. 1 plus 4 plus 5, 10 plus 8, 18. 18 plus 18, 36 divided by 6, so it's equal 6. Okay, then we should also calculate Ex variable. Let's just calculate the skewness first. Skewness is X. Let's just calculate the mu3 first. Where's my pen? Here. Let's calculate mu3. It's equal sigma I xi. This is just formula over m. And here you can 1 minus 6 to the third power and 4 minus 6 to the third power plus 5 minus 6 to the third power. It's etc. until the last one 10 minus 6 to the third power divided by 6. And here we can get this mu3 is equal to negative 9. So the skewness, okay, to calculate skewness, we still need to calculate the variance. Now, VARX is equal, similar, it's just instead of third power, we use the second power, xi minus x bar, the second power. Now, this, I think once you calculate 9, from here we can get the skewness is mu3 over square root of variance. Skewness is so it's negative. Okay. The last question is asking the unbiased sample variance. So we already calculated variance VAR x unbiased s squared. The easiest way is just using the formula because they are the same, similar calculation. Just one is divided by n, the other one is divided by n minus 1. So from here you can easily get n times 9. So you can get 10.8. So that's the unbiased sample variance. Of course, you can also just follow the original formula to calculate that.